So I'm just going to pick up where we left off last time. We had defined the definite integral, and we say that a function is integrable if that definite integral exists. What does the definite integral mean? The definite integral of a function over an interval from a to b means you chop up the interval from a to b into subintervals. So that's a partition. And for each subinterval in your partition, you pick a sample point. You evaluate the function at the sample point. You multiply by the width or length of the relevant subinterval, and then you add all those together, and you take the limit of those sums, those Riemann sums, as the mesh of the partition. So the length of the longest subintervals approaches 0. And if the limit that you get is independent of how you took the partitions and how you pick the sample points, then we say that that function is Riemann integrable. Not all functions are Riemann integrable. You can define some weird functions that are not, but we're going to deal mainly with Riemann integrable functions in these lectures and in this book. So we've looked at the interpretation of the Riemann integral in terms of area, and now I just want to, we need to look at some properties of the integral. So it's a theorem that suppose f is integrable on the closed interval from a to b. I am assuming a is less than b, so that this is not the empty interval from a to a, or the interval containing one point from a to a. Suppose f is integrable on ab and cd, where c is less than d, is another, or doesn't have to be another, is an interval contained, could be the same, contained in AB. Then, as you might suspect, if f is integrable on this bigger interval, then f is integrable on the smaller interval. That is in fact true. Then f is integrable on CD. Also, part of this, if A is less than C is less than D, then, well, then we know, I meant B. A is less than C is less than B. Well, we know then that from this first part that f would be integrable on the closed interval from A to C. We also know that f would be integrable on the closed interval from C to B. Is there any relation between the integral on the interval from A to B and those on A to C and C to B? The answer is yes. And you might be able to guess this too. Then the integral from A to B of f of x dx, you can split that up. You can first go from A to C and then go from C to B. In terms of area, this is kind of intuitive. This is intuitively obvious, especially if you take f to be positive, so it's easier to draw this case, discuss it, than if you allow f to be positive and negative. Positive some places, negative other places. So the standard kind of picture for this would be, here's some function, here's A, here's B. The integral from A to B is represented graphically by this area under the curve and above the interval from A to B. So that area, all this area equals the integral from A to B of f of x dx. But then if you take some c that's in between, well, then the area breaks up into two pieces. There's this area, and there's this area. And yeah, all we're saying is this area from here to here is this area, the integral from a to c of f of x dx, plus this area, the integral from c to b of f of x dx. So geometrically, in terms of area, this is obvious. We're not going to prove this, but it's supposed to be intuitively clear. All right. We like this property so much that we can split up integrals at any point between a and b that we'd like for it to be true regardless of the order that a, b, and c are in. So we're going to extend our definition of what the integral means and what integral notation means just so we can have this property be true no matter what order a, b, and c are in, and even if a, b, and c are equal. So we want the integral from a to b of f of x dx to equal the integral from a to c of f of x dx plus the integral from c to b of f of x dx, regardless of the order of a, b, and c. Understand, at this point we have only defined the definite integral over an interval from a to b, and where b is greater than a. So we don't know what this notation means if b equals a, and we certainly don't know what this notation means if the lower limit of integration is greater than the upper limit of integration. So, but we're going to define what the integral means in those cases just by the fact that we want this formula to be true regardless of what a, b, and c are, as long as f is integrable over all of the relevant intervals. So what do? Well, suppose you pick c to be a in this formula. We want the formula to be true even if c equals a. So we want the integral from a to b of f of x dx to equal the integral, if c is a, we get the integral from a to a of f of x dx plus, and if c is a, so we want this to be true. Well, here's the integral from a to b, here's the integral from a to b. We would need for the integral from a to be 0. So we make that definition that if your upper and lower limits of integration are the same, we define that definite integral just to be 0. In terms of area, this makes sense because the integral from a to a, what's the area under the curve and above the interval just between a and itself? Well, there's no area. You have this straight line. It doesn't have any area. So yeah, the integral being 0 agrees with our area interpretation. So we define. This is just definition. The integral from a itself of any function is just 0. All right, good. So how do we define things if the lower limit of integration is bigger than the upper limit of integration? So all right, so we want this formula to be true regardless of where we split things up. And it doesn't matter if you call things A, B, and C. In particular, it means that, oh, suppose we integrate from A to A of f of x dx. Well, we know that we've just defined this to be 0, but now we're supposed to be able to split this up any way that we want. So we could go from A to B, and then go from B to A. Right? All that, you shouldn't get caught up on the letters A, B, and C here. All it says is if you go from A to B, you should be able to go from A to any place else and then pick it up. It's like you go from here to here, and then you go from here to here. That's the same as going from here to here. That's what I've said, that going from A to itself should be the same as going from A to B, and then from B back to A. But this is 0. Right? We've just said that this has to be 0 to make this formula true in all cases. And so we define this to be 0. So if this part's 0, then we need the integral from A to B plus the integral from B to A to be 0. In other words, the integral from B to A of f of x dx needs to be negative the integral from A to B of f of x dx. And we make that definition. This is how we define things. If A is less than B and f is integrable on AB, we define the integral from B to A of f of x dx to be negative the integral from A to B of f of x dx. This is a little more difficult to interpret in terms of area. It's just you should think we integrated kind of in the wrong direction. So that's why you get the minus sign. It's like you count this area from A to B with a minus sign because you went from B to A. But really, you should just realize, whether you interpret it as area or not, that just to make our formulas work out nicely, we define the integral from a larger value to a smaller value to be negative the integral in the other direction. Okay. Other properties of the definite integral that follow quickly from its definition as a limit of Riemann sums. We're not going to prove these, but one is, so these are very important. The definite integral is linear. Just as the indefinite integral was linear and differentiation is linear, i.e. this means that if you integrate from A to B of some constant times a function plus some other constant times another function, then you can split up the sums and pull out the constants. Maybe D is a bad choice here. How about E, F, G, H? All right, how about P and Q? So these are constants. This splits up. You can split up the sums and pull out the constants. Why is this true? Because you can do it for summations. Summing is linear. You can split up sums and pull out constants. And definite integrals are just a limit of sums, and that's why this is true. You get P times the integral from a to b of f of x dx plus Q times the integral from a to b of g of x dx. I've left out some important words. It's that suppose f of x and g of x are integrable on AB, then so is this function, and its integral in terms of the other two are given by this. So I should put those in. So, right, this really should be before I wrote this equality. I should put this up here. The definite integral is linear, i.e. if f and g are integrable on AB, then so is this linear combination. That's what a constant times something plus a constant times another thing is called. This linear combination of f and g, and then this formula holds so that everything in it is defined. In general, I frequently will write equalities, and I always mean to be assuming when everything is defined. So really, all right. That's nice. It helps us split up more complicated integrals, complicated looking integrals into easier pieces. And then another one that's kind of intuitively obvious or intuitively clear is, so this is called linearity. We need to refer to this, linearity. This one is usually called monotonicity, which is kind of a frightening term. That's what it's called, theorem. Monotonicity. Monotonicity. And it says if for, once again, I'm assuming A is less than B, if for all x in AB, f of x is less than or equal to g of x, then, and once again, and f and g are integrable on AB, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Right? What we've said is if one function is always less than or equal to another one on the interval and both functions have integrals that exist, then the smaller function has to have a smaller integral. Why? Well, because when you take a partition, if you evaluate f and g at the same sample points, the f1 will always be less than or equal, each f evaluated at a sample point will always be less than or equal to g evaluated at the sample point. And the delta xi's are always positive. So, of course you'll get this. In terms of area, this is kind of blatantly obvious too. It's you've got some function. Here's y equals g of x. And maybe f is bigger than g over here somewhere. But, so here's y equals f of x. But maybe a and b are here. So that on the interval from a to b, the value of f of x is, in my picture, strictly less than the value of g of x. But certainly it's less than or equal to it. And what we're saying is then that the f integral, which would be represented by this area, is less than or equal to the g integral, which would be represented by that area plus this area. So, of course, that integral, in my picture, that integral would be strictly less than this. So this is called monotonicity. It's important. But the big theorem is, you may have noticed that every time I've been drawing functions and drawing graphs of functions and discussing the area, I've been drawing continuous functions. This is the big theorem for what functions are integrable. There are generalizations of this and variations on this, but the big fundamental one is theorem if f is continuous. On AB. And again, I meant A is less than B on AB, then f is integrable. So this means that all these things I've been talking about for integrable functions like linearity and monotonicity hold for continuous functions, and the graphs I've been drawing had been of continuous functions. This is nice. In fact, you can be a little more general than this. F is allowed to have a finite number of places where it's not continuous, and then it's still integrable. Well, actually, I need to say more words. That would be as long as f is bounded. So we'll leave that more general discussion for later. But this is the big fundamental case, that continuous functions are integrable on closed intervals. So what are some basic integrals that we can do before we have some theorems to help us? The big theorem to help us calculate is called the fundamental theorem of calculus. But right now, we can calculate some other integrals using geometric considerations and using some of our summation formulas from earlier sections. So, for instance, what is the integral? So, once again, I'm going to assume that a is less than b. What is the integral from a to b of 1 dx? Well, we can look at this in terms of area. Here's the graph of the function that's always 1. And between a and b, what's the area under that graph and above the interval from a to b? Well, it's its height, which is 1, times its width, which is, its width, which is b minus a. So b minus a times 1, so just b minus a. Okay. Let's try something slightly more difficult. What's the integral from a to b of x dx? graphically, you would take, so maybe I'll put it over here. So the integral from a to b of x dx. Well, graphically, you would take y equals x. So here's y equals x. And you want the area from a to b. Now, I'm just going to do this assuming a and b are both positive. I leave it as an exercise for you to check what happens when a and b are both negative, or when a is negative and b is positive. But the formula we get will work in all of those cases. So we want this area. Oh, but we know how to calculate areas of things like that. That's a trapezoid. So a quadrilateral with two parallel sides, the area of such a thing, 1/2 the sum of the bases. The bases are the parallel sides. 1/2 the sum of the bases times the height. The height is the perpendicular distance between the two parallel faces. That would be this distance right here. So this is the height. Even though, yeah, in our picture, you'd have to turn your head sideways to think of it as the height. But, so we get 1/2. Well, what's this height? Well, this is the graph of y equals x. If x is a, then this y coordinate is a. So that height is a. What's this height? It's b. So that's the sum of the bases times the height, which is b minus a. But then we have b, this is the same as b plus a. B plus a times b minus a, use the difference of squares. This is 1/2 b squared minus a squared. So that's what we get. 1/2 b squared minus a squared. Okay. What about something more complicated? So what about something like, what's the integral from, well, why don't we put in some numbers? What's the integral from 1 to 3 of 5x minus 7 dx? What do we do? Well, the definite integral is linear. We can split up the sums and pull out the constants. This is, I'm going to think of, actually let me rewrite it. I'm going to think of that integrand as 5x minus 7 times 1 dx, and then you get, this is 5 times, so you split up, oh, sorry, I am going to think of this as plus a negative 7 times 1. You split up the sums, you pull out the constants, you get 5 times the integral from 1 to 3 of x dx, plus negative 7 times the integral from 1 to 3 of 1 dx. Notice that, yeah, I wrote this as plus and negative. That's because in my statement of linearity, I said you could split up sums and pull out constants, but of course you can always consider the constant to be the negative 7, to include the minus sign, and then it means you can also split up differences. So from now on I probably won't actually write it as the sum of negative. I'll just say, oh, you can split up this difference also. So you get 5 times, oh, but we have a formula for this. It's that squared minus that squared times a half. So we get times 1/2 3 squared minus 1 squared for this part, using our formula that we just developed for the definite integral of x dx. And then minus 7 times this, was just b minus a. So you get 3 minus 1. And so this is what you get. You can simplify this, but it doesn't matter. This is what you get for the definite integral. We have these fundamental building blocks of the integral of x dx and the integral of 1 dx, and we put those together to do this one. All right. What about something that looks a lot worse? What is the definite integral from 0 to 5 of the square root of 25 minus r squared dr? All right, let me not use r. How about let's use something different. How about a t squared dt? How are we supposed to do this? Well, this is certainly a continuous function on this interval. So a definite integral exists by theorem, but that doesn't help us calculate. In fact, we only have we have a couple of ways to calculate. One is by geometry and knowing areas and interpreting the integral in terms of area. And the other one is we actually would have to take partitions, at least a sequence of partitions, whose meshes approach 0, and then we'd take sample points and take the limit of Riemann sums. Because of the theorem, we know this integral exists, so that if we take a limit using partitions whose meshes approach 0, whatever limit we get has to be this one. We don't have to worry about taking every possible partition. The theorem already tells us that, that you get one value regardless of how you take the partition. So if we just take one sequence of partitions with the meshes approaching 0, we could do this. But we'd rather not because it's painful. So how do you do this? Well, hopefully you realize that this function is part of the graph of that is part of a circle. If you square both sides, you get this, or what's the same thing, t squared plus y squared equals 25. But by taking the square root, you only get positive y values, or non-negative y values. So the graph of that function is the top half of a circle of radius 5 centered at the origin. But the integral is only looking at t values between 0 and 5. So we're looking at this area right here. Oh, well, that's the quarter. A quarter of an area of a circle of radius 5. But you know the area of a circle. So we've got 1/4 of the area of a circle, pi times the radius squared. So pi times 5 squared. So that's what you get. Okay. Why don't we do one where you have to calculate limits of Riemann sums? So suppose we want the integral from 0 to b of x squared dx. This certainly exists. X squared is continuous. The graph of y equals x squared is a parabola. And we're just asking, in terms of area, we'd like to know this area. Well, too bad. We don't have any nice formulas from high school geometry that will help us with this, or at least I didn't learn any in high school geometry that would help me with this. So we just have to take a limit of Riemann sums. There's no real choice. We know that the integral exists because y equals x squared is continuous. So we don't have to worry about, oh, let's take left Riemann sums and right Riemann sums and midpoint Riemann sums and make sure no matter how we pick the sample points and no matter how we pick the partitions, the limits all get to the same thing. We're appealing to the theorem to know that this is a continuous function and so the integral exists. And so we have to get the right limit if we use any sequence of partitions whose mesh approaches 0. So we will pick a partition sub n. So for each n, we're going to have a partition. I'm going to partition the interval from 0 to b into n equal subintervals, subintervals of equal length. So we're taking 0 to b, and I'm going to partition it into n subintervals of equal length. That means, so each subinterval, n subintervals of equal length, in subintervals of equal length, what would that equal length be? Well, the whole length is b minus 0, so b. And then, and you want n subintervals, so they'd all have length b divided by n. Now, I am assuming in this picture that b is greater than 0. You can do the same thing if b were over here somewhere. The formula that we get will be correct, but I'll leave that as an exercise. The length would now be negative. If you took b to be negative, the length here would be negative b, and you make all the corresponding changes. All right, n subintervals of length b over n. Great. That means that our partition, p sub n, we're doing this for each natural value of n, so n equals 1, 2, 3. You'd start at 0, and then you always go up by b over n each time. So b over n, 2b over n, all the way up to n minus 1 b over n, and then finally nb over n, but that's the n's cancel and you just get b. So this would be our partition. We're going to take the left. Let's take the right. Let's take the right sample point. So we'll do the right Riemann sum. Our sample points in each subinterval will be the right endpoint of the subinterval. So what does that mean we'll get? That means our first sample point is b over n, and then that also goes up by b over n each time. So it looks exactly like the partition, except we don't have 0 there. So what this means is Si is just I times b over n. So the ith sample point is just I times b over n. So for instance, when I is 1, you get b over n. When I is n, you get b. And we need to calculate the limit of Riemann sums. We know that this will exist because we know the definite integral exists, and as n goes to infinity, certainly the length of every subinterval, so in particular the mesh of the partition, as n goes to infinity, the mesh of the partition is approaching 0 because b is fixed, n goes to infinity, the mesh of the partition is approaching 0. So we want to look at the limit as n goes to infinity of these Riemann sums. So the sum as I goes from 1 to n of f of Si times delta Xi, where f is the squaring function, the function that's our integrand in the definite integral. Well, this is the limit as n goes to infinity, the sum as I goes from 1 to n of f is squaring, Si is Ib over n, so we get Ib over n squared. That's this. And then delta Xi. Delta Xi is the width of the ith subinterval. All the subintervals have equal length, b over n. So we need to sum this. But b over n is a constant. It doesn't depend on the index I, so we can pull that out of the summation. Not outside this limit, but outside this summation. In fact, we can square inside there, so what we get we get the limit as n approaches infinity of, well, there's also a b squared over n squared here. So there's a b cubed over n cubed that we can pull out. So you get a b cubed over n cubed. But what you can't pull out of the summation, can't factor out, you'll be left with an I squared inside here. So it's times the sum as I goes from 1 to n of I squared. Now, we need a formula for the sum as I goes from 1 to n of I squared. But we have such a formula. We had it in an earlier section. This is the limit as n goes to infinity of b cubed over n cubed times this is n times n plus 1 times 2n plus 1 over 6. Should you have that memorized? No, absolutely not. You should go back and look it up. But that's what you get. So for instance, when n is 1, we should get 1 squared. So we better get 1 when we put that in here. When n is 1, you get 1 times 2 times 3. That's 6 over 6. 1, yeah, so it works then. Or maybe we should do one more just to make sure. So for instance, when n is 2, you would get 1 squared plus 2 squared. So that should be 5. Is that really what we're getting when n is 2 here? We get 2 times 3, that's 6, times 5, then the 6's cancel 5. Yes! So, all right. We're convinced that we wrote the right formula. I'm convinced. So, but now we need to calculate this limit. Well, the b cubed doesn't depend on n. We can pull that outside the limit. So this is the limit as n approaches infinity. I just said we'd pull b cubed out of the limit. I didn't do it. B cubed times the limit as n goes to infinity of what? All right. We're left with this divided by n cubed. I'm going to take that divided by n cubed and divide each of these factors by one of the n's. So I'm going to split up dividing by n cubed is dividing that by n, dividing this by n, and dividing this by n. N divided by n is, well, I'll go ahead and write it. You get this, then we get n plus 1 divided by n, and then you get 2n plus 1 divided by n, all over 6. But what is this? N over n, definitely 1, so those cancel. This, n plus 1 over n, you write that as n over n plus 1 over n. That's 1 plus 1 over n. So you get 1 plus 1 over n. Again, here you split this up. It's 2n over n plus 1 over n, but 2n over n is 2 plus a 1 over n. So you get 2 plus 1 over n. But now it's clear what happens as n goes to infinity. As n goes to infinity, 1 over n approaches 0. This 1 over n approaches 0. So these terms go away, and you get 2 over 6, so a third. So we get b cubed over 3. Great. What was all that? That was this definite integral. It's the area under this graph. If b is positive, anyway. This is b cubed over 3. I want to say a couple of more things about this. One is that, yeah, if b is negative, so could this formula be correct when b is negative? Right? We drew the pictures, we talked about it in the case where b is positive. Could it even be correct when b is negative? For instance, could it even be possible that the integral from 0 to minus 2 of x squared dx is minus 2 cubed over 3? Well, this is a negative number. How could you get that for an area? You can't get that for an area. Oh, maybe our function is negative, so it should be area with a negative sign. No, Well, yes and no. The function y equals x squared is positive over here also. So the integral should be giving us an area. But what the integral? This integral, if b is negative, this integral is in the wrong direction. The limits of integration are in the wrong order. So yes, the integral from -2 to 0, the integral from -2 to 0 of x squared dx would give you the area under the curve. But the integral from 0 to -2, as we said, by definition, is negative the correct integral. Does that give us the right thing here? Yes. Because by symmetry of the graph y equals x squared, this area between under the graph and over the interval from -2 to 0 should be the same as the area under the graph over the interval from 0 to 2. So what I'm claiming is that just by symmetry, you can conclude that this integral is the same as this integral. Right? Just by symmetry. And in particular, I'm claiming that let's pick a neutral letter. If a is positive, then this is true. If a is positive, negative a is, of course, negative, so this is in the correct direction. It goes from a smaller number to a bigger number. Yeah, and those areas are the same. Great. So what? Yeah, so it means that the integral from 0 to -a would be negative this area. But that's exactly what we're getting. Right? This is, when you cube -2, this is negative 2 cubed over 3. So negative 8/3, which is negative the integral from 0 to 2 of x squared dx. So yeah, this formula is right, even when b is negative. It's giving you area, but with a minus sign, not because the area is below the graph, but because if b is negative, this integral is in the wrong direction. It goes from something bigger to something smaller. All right, as a last example, no, there was one more thing I want to say about that. I only calculated the integral from 0 to b. What if you wanted to go from a to b? So we now know the integral from 0 to b of x squared dx is b cubed over 3. What's the integral from a to b of x squared dx? Do we need to do another limit of Riemann sums argument? No. We can use our general properties of integrals to get this one just from this one, because we can integrate from a to 0 of x squared dx and add to that the integral from 0 to b of x squared dx. So and then the integral from a to 0 is negative the integral from 0 to a, so this is negative the integral from 0 to a of x squared dx plus the integral from 0 to b of x squared dx. But now we can just use the formula on both of these. So we get negative, this one is the integral from 0 to a. That's like the integral from 0 to b, except we've got an a. So we get negative a cubed over 3. And then this one is plus b cubed over 3. So yeah, we get 1/3 b cubed minus a cubed. All right, one last thing. We talked about a rod with variable density and a fixed cross-sectional area. And we had a pretty simple density function because we didn't know how to integrate much. At this point, we could give ourselves a slightly more significantly more complicated density function, and we could also change exactly how much of the rod we care about. So once again, let's take a rod of fixed cross-sectional area A. And just to have some units, I'll say in square meters. So I'm assuming that that cross-sectional area is a constant throughout the rod. And I've got this rod lying along the x-axis, and it's 1 meter long. So 1 meter. And I'm assuming that the density of the rod at any point at x-coordinate x, I'm assuming that at each point at a fixed x-coordinate, the density in kilograms per cubic meter is the same for a fixed x. And I'm going to now pick something more complicated than what we had before. I'm going to pick this. Yuck. And the question is, what is the mass of the rod? Between x equals a quarter and x equals a half. These are in meters, of course. A quarter of a meter, half a meter. All right, well, what do? If this is a quarter and this is a half, what we want to do is add up all the little blobs, add up all the little chunks of mass in this region. So it's what we did before. Yes, we should really talk about Riemann sums, but we do that when we have to prove something, like when we just calculate a limit of Riemann sums. But for these physical problems, what you do is, or the nicest thing to do, is to talk about this in terms of infinitesimals. So yeah, you're at some x-coordinate, and you imagine an infinitesimally small interval, which I can't draw ridiculously small, or we wouldn't see it, but you think of it as being infinitesimally small. And here's this little chunk of volume. So this has some volume. So what's the mass of this little chunk? Well, the mass, it'd be an infinitesimal chunk of mass. It's density times an infinitesimal little chunk of volume. I didn't say it this way before, but it's an infinitesimal chunk of volume. I wrote the density at x. Which x-coordinate in here? The only one. Whatever x-coordinate we started with, because this is an infinitesimal interval, and we're thinking, there's only one true x-coordinate in there. This is just a way of thinking. Really, you're supposed to take sample points and limits of Riemann sums, but this is a very nice way to think about it. So what do? Well, so this is density times what's an infinitesimal little chunk of volume? Well, it's the cross-sectional area times an infinitesimal change in length. So this is just a times dx. Great. So, and what do we want to do? We want the mass that we're looking for, the mass between x equals a quarter and a half, should just be you add up all of the little chunks of mass as x goes from 1/4 to 1/2. So we write this. The limit as x goes from 1/4 to 1/2 of dm. You think of the integral as a continuous sum of all these infinitesimal contributions of mass. The limits of integration, if we didn't write x equals, they're supposed to describe what that variable does. We don't mean the mass goes from 1/4 to 1/2. We mean x does, so really you need to write in the x equals. But then you quickly replace this with dm is delta x times this cross-sectional area times dx. And now that you have the right variable in your integral, you can just put 1/4 and 1/2. And you put in what delta is. I picked 5 plus 7x squared. All right, so this is what we need to calculate. This definite integral as x goes from 1/4 to 1/2, 5 plus 7x squared times a times dx. But a is a constant. 5 and 7 are constants. We can split all this up. So for instance, you can pull out the a first since it's multiplied times everything. This is linearity, and we're about to use linearity again and split up the 5 and the 7x squared. So you get a times what? The integral? 5 times the integral from 1/4 to 1/2 of 1 dx plus 7 times the integral from 1/4 to 1/2 of x squared dx. But we know this integral and this integral. We get a times 5 times. And our formula for the integral of 1 from a to b, you just take b minus a. So you get 1/2 minus 1/4 plus 7 times our formula for the integral of x cubed from a to b. You get b cubed over 3 minus a cubed over 3, or it's the same thing, 1/3 of 1/2 cubed minus 1/4 cubed. This would be the total mass of the rod in that region. We don't have a number for a, so we can't actually get a number. This is in kilograms. Right? If we had a, we'd be able to finish, get a number. But, oh, I left off a cubed. Minus 1/4 cubed. If we had this capital A, we'd be able to get a number. But this is what you do. And I mean, this is kind of our goal, to have formulas for basic integrals, just like for derivatives. We knew some basic derivative formulas, and we put those together to take derivatives of more complicated things. We want some nice integration formulas, and we put those together to do more complicated looking ones in more complicated applications. Of course, we don't want to take limits of Riemann sums. And the number one way we're going to get formulas, nice formulas for definite integrals, is by the fundamental theorem of calculus, which will tell us how the definite integral is related to the indefinite integral, the antiderivative.